Good morning, everyone, and welcome to the last day of the conference. And Eran Assaf from Dartmouth, definite orthogonal modular form in rank 4. Take it away.
Thanks, Alex, for the lovely introduction. I'd like to thank the organizers for the great T-shirts and for inviting me to speak here. And also thank you all for coming on Saturday morning. You know, it's difficult, first talk in the morning, and then there's a title that you don't understand, but I ask you to bear with me. It'll take some time, but I'll get to what it actually means. But if there's anything else that you don't understand during the talk, then like Edgar said yesterday, please stop me and ask Edgar. It's very important. Okay, I'll start with some motivation. Well, maybe if I get it to work. Yeah. Okay, so my motivation will come from the Foursquare.
Start working?
Yeah, it started working. Okay. Thanks. My motivation comes from Foursquare. The kids don't like it anymore. They prefer the Gagapit. But no, I meant like the representations of numbers as sums of four squares. And even saying that is not enough because there are too many Foursquare theorems, but I'm referring to Jacobi's Foursquare theorems. So we're actually counting the number of representations as a sum of four squares. This is a very famous classical result. You can just count it by counting divisors of our number. And I'll give a brief overview of how one proves this theorem. So there are many proofs, but the idea is to write a generating series, write a theta series, and coefficients are just these representation numbers. And then we find some finite dimensional vector space in which this generating series lives. And finite dimensional vector spaces are fun because if we can find a nice basis for this finite dimensional vector space, we can just represent our generating series in that basis, compare coefficients, and get the result. Now, I want to say something more about this finite dimensional vector space and how we find it. So that will take a little longer, but since this is a modular forms talk, I'll have to draw the gang sign. You all know the gang sign of modular form talks? No? No? Okay, so this is the upper half plane. This is just complex numbers with positive imaginary part. Now, it has a natural action by 2x2 matrices. Okay, just by linear fractional transformations. And you can see two of these over here, very simple ones. Right? I can just take any number, any z to z plus 1, any other number z to minus 1 over z. These are matrices with integral entries. More generally, we will sometimes want to consider some discrete subgroup of 2x2 matrices. And if I'm looking at the quotient, I identify every 2 points here that I can move one to the other using this discrete transformation. So, with the example of transformations over there, if I start with some point, say here, is that visible? Excellent. I can move it using z plus 1 over here, and then over here. And if I'm inside, this might not be visible, but if I'm inside the unit circle, can you see this? Okay. If I'm inside the unit circle, I can use the other transformation, minus 1 over z, to move myself somewhere here. Yeah, maybe it will be further away, say, here. But if I landed here, I can still move myself again with z plus 1 over here. I have this nice orbit. But I can always make sure I end up between these two lines, minus half and a half, and above the unit circle. So if I'll just erase everything else, you'll get the gang sign, which is just the quotient of the upper half plane by the action of SL2Z. And again, we have to notice that here, this side is identified with this side, right? Because we can move them one to the other with Z+1. And we also have an identification with this half, because they move one to the other with -1/Z. Okay. But we will also be interested in other discrete subgroups, and there will be ones that will play special role. So these are gamma 0n and gamma 1 of n. So these are just matrices where the bottom left entry is divisible by n. And gamma 1 of n are those where the diagonal is 1 modulo n. And we might want to notice here that this gamma 1 of n is the kernel of a homomorphism, a very nice homomorphism of groups into Z mod n star, which is an abelian group that will come up later. Now, when we form this quotient, we see that it's not compact. It goes up to infinity. And that's sometimes a problem when you're trying to do geometry. So we compactify it. And the usual compactification is using cusps. Here we have one cusp at infinity. And because not like Avi, my drawing abilities are limited to two-dimensional things, I will not try to draw the actual three-dimensional object that we get when identifying all these things. But luckily, we have, each one of you has a visual aid. You see the lines here and the two parts of the circle. So when we add the point at infinity, we compactify. And if we look at the identification, these two close, and these two are identified. And at least topologically, you can believe that one gets a sphere. Now, the nice thing about these spaces is that they're actually compact Riemann surfaces. So not only topologically it's a sphere in this case, it also has a complex structure. Okay, I can provide it with complex charts, with holomorphic charts that make it into the Riemann sphere. More generally, for any discrete subgroup, that's true. You'll just have to accept it as a fact. Here's an example of how we make this one a compact Riemann surface. Just what is the chart around the point at infinity? So this is the very well-known Q, which is e to the 2 pi I z. Okay, it uses the fact that z is identified with Z+1. Okay. So now we will assume that gamma is torsion-free. For our purposes, it will be enough. And we can look on this compact Riemann surface. This is a complex curve. It has holomorphic differentials on it. And we can consider the holomorphic differentials that have at most simple poles at the cusps. So they're holomorphic everywhere but the cusps. And at the cusps, we allow for simple poles. For example, in this case, we only allow for a simple pole at infinity. Of course, if you know some complex analysis, then you'll know that there is no holomorphic function with only a simple pole at one place on a Riemann sphere. But more generally, if we have any discrete subgroup, we can look at this vector space of differentials. And it's a classic result due to Riemann. And this is a special case of the Riemann-Roch theorem, that the dimension of this space of differentials is given by this simple formula. So basically, the idea this G, the genus of our curve, is the number of holomorphic differentials, the differentials that are holomorphic everywhere. And we get an extra dimension for every cusp because we can control the residue. It gives us another degree of freedom. But the sum of all the residues must sum to 0. So we lose 1 degree of freedom. That's the formula here. Now, many times when you see a modular form talk, you see a completely different definition of modular forms. So I'd like to make the connection between these two. And the idea is that this space is very nice in the sense that we know its universal cover. the upper half plane is simply connected. And this is the quotient of the upper half plane. So if we have any holomorphic differential on this space, we can pull it back to the upper half plane. And it will be of the form fzdz. So we can identify our holomorphic differential with this function. But when we translate these properties of the differential to the properties of the function, we get something slightly more complicated. So here's an example for this kind of curve. Near infinity, we can represent our holomorphic differential as a function of q, our local coordinate from before. If we pull back, then we get 2 pi I q just by differentiating this q, right? It's multiplied by 2 pi I q. And we see that if we had a simple pole at the cusp, then our function f will actually be holomorphic at this cusp. And if we were holomorphic at this cusp, our function f will actually vanish at the cusp. So this really identifies the space M2 of gamma with holomorphic functions f, and we want them to be invariant under gamma, right? We had something invariant under gamma, we pulled it back. So we want the differential to be invariant under gamma, and it's a nice exercise to see that the derivative of this linear fractional transformation is cz plus d to the minus 2, and that gives our usual nice formula for modular forms, in this case of weight 2 and level gamma. So this is what I call in this talk the space of modular forms. It's level 2 and weight gamma, level gamma and weight 2. And we will also be interested in the subspace of holomorphic differentials, which, as I said earlier, are the ones that vanish at the cusps. Now, this subspace is called, because they vanish at the cusp forms. This is the space of cusp forms. Okay, remember that I told you that gamma 1 was the kernel of some homomorphism into Z mod n star. So we will also need to consider this isomorphism, because this group acts naturally on our space of modular forms for gamma 1. We can just act with an element of gamma 0, and because of the gamma 1 invariance and the fact that it's a normal subgroup, we will see that we still have a modular form for gamma 1. And this is an abelian subgroup acting on a finite dimensional vector space. So we can just decompose according to its characters. And its characters are known as Dirichlet characters. And we write M2 n chi for the subspace of M2 gamma 1 of n of the functions with character chi. So that means that they will transform according to this formula. And we just twist it by a character. It will just appear later on. So I'll say it right now. But now let's get back to our original problem. So for that, I want to consider specifically the curve x0 of 4. So one can compute, that's a nice exercise, that the cosets of gamma 0 of 4 inside SL2Z, there are 6 of them, and they are given by these elements. So we have beta, s, alpha. Alpha squared is just replacing this 1 over here with a 2. And alpha inverse is replacing this 1 with minus 1. And we can write the quotient of the upper half plane by gamma 0, 4 by using this image and these coset representatives, right? Because every element will be up to some coset representative here in this domain. So here's an image. Can you see what's going on here? So we had this fundamental domain for SL2Z. We translate it by S, which is minus 1 over Z, to this domain. We use alpha to move it here, or alpha inverse to move it to the other side. We can use alpha again to move it here. And if we apply beta to this part, we get this weird triangle in the end that seems to ruin all the symmetry. This lovely picture. But we see several things. So first we see that we have a cusp at 0, and we have a cusp at 1/2, other than the cusp at infinity. So we actually have 3 cusps in this picture. And we can also see the identifications. This side is identified with this side. This side is identified with this side. And if you think about it carefully and try to see what one gets after all these identifications, you'll get a spaceship. Right? Because these 2 A1s that were glued together give you a sort of a cone. And it happens in every cusp. And in the middle, we get a sphere. But topologically, this is still a sphere. And because we know it has a complex structure, it's a compact Riemann surface with no holes, then we know it's actually, well, isomorphic to P1. So I know it might seem weird that we have these, at the cusps, we have things that look like singularities. That's related to the weird metric on these spaces. They're all hyperbolic, and there's really no singularity here. So we compute that we have 3 cusps, and that this is actually a Riemann sphere, so the genus is 0. So by the Riemann-Roch theorem, we know that the dimension of this space of modular forms for this discrete subgroup is just 2, 3 minus 1. Okay, so it's a 2-dimensional vector space. On the other hand, if you remember the function theta from before, but now we think about it as a function of z, where q is our local coordinate at infinity. So this function satisfies nice transformation property. For example, it's invariant under translation by 1, right? Because it's all the sums of q to the n, where q is e to the 2 pi I. And it also satisfies this transformation property, which is a little more hard work, but you'll have to accept my word for it now. And the reason that it interests us is because these 2 matrices, 0, of course, 1, 1, 0, 1, and 1, 0, 4, 1, actually generate, well, up to a sign, generate this group. So if we know these 2 transformation properties, we know that theta is actually a form in our space, in our finite dimensional vector space. So how do we finish the proof of the 4-square theorem? Well, we construct some series, which is easy to construct. Here, sigma n is just the sum of divisors, which is almost in this space. We have to make some corrections. That's some work, but one can show that these 2 functions actually lie in our vector space, and they're linearly independent. And now, from the first 2 terms, we can write our theta function as a linear combination of them, and just some simple algebra and equating coefficients give us the result. More generally, if we have quadratic form in 4 variables, not necessarily sum of 4 squares, we could have products of any 2 of the variables, we still can consider the representation numbers of these quadratic forms, and we can still form this theta function, right? This generating series for this quadratic form, same as we did with the 4 squares. And it's still a modular form living in some finite dimensional vector space. So this is a very classical and well-known method to investigate quadratic forms. But I would like to look at it slightly differently from the point of view of lattices. So suppose I have some some quadratic form. And from now on, we will assume that our quadratic forms are of rank 4 and that they are positive definite. That will just make my life easier. So we can associate to any quadratic form, we can associate a bilinear form called its polar or Gram matrix. And I will consider integral lattices. So these are lattices that the quadratic form takes integral values on. And we will denote by the discriminant of the lattice the determinant of this matrix, which will be some integral number. So given a lattice, we can construct the associated theta series, which is the same theta series as before, only before we took the lattice just z to the 4. The level of lambda is the smallest n that gets the dual of this lattice into itself. Then in general, this theta series always lives in the space of modular forms with level determined by the level of the lattice and character determined by the discriminant. That's a general fact. Okay, so it seems like we solved the problem of... Oh, thanks. It seems like we solved all the problems possible, right? We have a quadratic form, we just form its theta series, we know everything about it, right? Seems like a nice solution. But there's a problem. Oh, I waited too long. Yeah, you're right. Thanks, Edgar. So we have a problem. This map, sending a lattice to its generating series, is not injective. So first, there's a silly reason that it's not injective. So let's take care of this one first. So if you think of all the transformation, the linear transformation that leave our quadratic form fixed, so these are just isometries from a vector space to itself, then it might map our lattice to a different lattice. So we say that two lattices are isometric if there is some orthogonal transformation with respect to our quadratic form that sends one lattice to the other. Okay, so naturally, if two lattices are isometric, they will have the same representation numbers, they will have the same theta series. Now, okay, so I can look at isometry classes of lattices. That will solve that problem. But I also want to find a nice finite dimensional vector spaces. And I want to tell you that even before we use the generating series, the theta series, we can find naturally defined finite dimensional vector spaces. So if I just want to distinguish between lattices, because my problem is lack of injectivity, I can look at a lattice and look at its completion at a prime p. Okay, I can look at lambda tensor zp for some p. If I have two lattices and they're different modulo p or modulo p squared or so forth, so they're different in zp, then I know that they're different. So our main problem is to distinguish lattices that are the same for every p, right? That they're everywhere locally isometric. So this is what we call the genus of a lattice. These are the set of all lattices in our vector space that are everywhere locally isometric to our lattice. So this is the smallest subset of lattices where we have difficulty of distinguishing them. So I want to focus on this part specifically. And because we only care about lattices up to isometry, we can take the isometry classes living in the genus. And this is known as the class set, and it is finite by geometry of numbers. If you think about it carefully, you also finiteness of the class number. And that's the same as this statement for binary quadratic forms. So the arguments of Minkowski translate very well to arbitrary dimensions. One can show that this set is finite. That was actually most of Minkowski's work was related to quadratic forms in that aspect. Okay, so I introduced this class set. It's a finite dimensional vector space. I haven't told you what it's good for, but first I would like to compute it somehow. So the main way to compute class sets is using the method of neighbors due to Kneser. And this is a very nice theory that it's also effective to compute the class method, and it will also give us something else called Hecke operators that will act on our space. I'll take some prime that doesn't divide the discriminant of the lattice. I can take 2. Prime 2 is fine. We say that 2 lattices are p neighbors if their intersection is of index p in each one of them. So if we have 2 p neighbors, we know, for example, that they're equal everywhere but p. Okay, they have the same discriminant, and the other neighbor is also integral if we started with an integral lattice, and it belongs to the genus. Now, it seems very, very abstract, but actually, p neighbors are quite easy to compute, so we'll see an example. But the main point here is that we can compute every element in the class set, every lattice, every other lattice in the class set, by just iterating this construction, by taking p neighbors of p neighbors, and we'll get to everywhere. So let's see an example of computing this class set. Suppose I'm given this quadratic form, very nice one. And here's the bilinear form associated to it. Okay, very small numbers, nothing gigantic like belly maps. Its discriminant is 29. And one can compute that the class number is 2, where the non-trivial class is just represented by these 2 neighbors. Okay, so we just find a basis in which we can multiply by 2 and divide by 2. That's all. That's all the 2 neighbor thing is. It's really very simple. And it has the corresponding quadratic form, again, you see, with very nice coefficients. And that's it. We found the class set. There are just 2 lattices in this class set. Okay. So now I want to tell you what orthogonal modular forms are. So this is a finite dimensional vector space, like the finite dimensional vector space of classical modular forms, that helps us with these kind of problems, with studying quadratic forms. So this is just, in our case, it's just the space of functions on the class set. Since the class set is finite, it's a finite dimensional vector space. And because we have these p-neighbor operation due to Kneser, we can define very natural-looking operators called the Hecke operators that will just sum over all the p-neighbors. So for every p, we define an operator Tp that takes our function and evaluates all the p-neighbors using that function. Okay, just sum over all our p-neighbors. Why is that a good thing? So all these Hecke operators commute, and they are self-adjoint. So they have a basis of simultaneous eigenvectors, which we call eigenforms. So this helps us diagonalize the space and have much more information about every little piece. Let's do an example. Let's see how it works. So this is, I took the smallest example. This is just the lattice of discriminant 121, and this is the smallest example with square discriminant, where something happens. So we have 3 lattices in the class set, in this case. Again, we can use p-neighbors to compute them. Let's write the representatives of the class set, lambda 1, lambda 2, lambda 3. And if we do the process above, we can get a basis of eigenforms. And I will write them like sums of these representatives. It just tells me, like, f2 is the function that on lambda 1 gives the value of 4. On lambda 2 is -6, and on lambda 3 is 9. Okay. So it's a convenient way to represent these forms. We can also apply the theta map and get a generating series for each of these functions, right? Because I can evaluate theta of lambda 1 multiplied by 4, right? I can extend linearly the theta map to these forms. And if I apply theta to F1, to this sum of all the lattices, I get this function, which some might recognize as an Eisenstein series of weight 2 and level 11. Right? Remember sums of divisors? So if you look at the coefficients here, you will see that it's the sum of divisors of these powers. And the second theta of F2 gives us something else, which is a cusp form of level 11. Nice enough. Now, I told you before about Hecke operators in this space. So if you compute the Hecke operators for F2, for example, we see that A2 is 4, A3 is 1, A5 is 1, A7 is 4. Can anyone find a connection or some relation between these numbers and this cusp form? It's tricky. It's not immediate, right? Okay, so maybe this A2 corresponds to 2, right? So here we have -2, and here we have 4. This A3 corresponds to Q to the 3, so the coefficient is -1. This is 1. If we go to 5, the coefficient here is +1, and A5 is 1. If we go to 7, the coefficient is -2, you get 4. Yeah, these are just the squares of these coefficients. That's very interesting. Maybe the most interesting thing is if you take F3 and apply the generating series, you don't get anything. You just get 0. Okay, this F3, if you look at theta of F3, you just get 0. So this is a stronger failure of injectivity. It's not just something related to global isometries. Okay, and when you think about it, it makes sense because classical modular forms classify binary quadratic forms, and we're looking at quadratic forms of rank 4. There is no way we will be able to classify them using the same spaces. But I want to first present another example. This was a square discriminant case, which was very well studied. And this is a somewhat less studied case where the discriminant is not square. So you remember our example with 29. There were only 2 lattices in the class set. Let's call them lambda prime and lambda. We can compute the Hecke operators in these spaces. Okay, it's just a 2-dimensional vector space. So all these matrices are 2 by 2 matrices. So for example, T2 is the left corner. This 1 is the number of 2 neighbors of the first lattice that are isometric to itself. And the 2 is the number of 2 neighbors of the first lattice that are isometric to the second lattice, so forth. So we compute these matrices, and again, we can compute the eigenforms. So one of them, as before, is just the sum of the 2 lattices, and we call it the Eisenstein series. Same as before, we saw that it generates the Eisenstein series. And the eigenvalues for all the primes are very nice. So you'll see that there's a difference whether the prime splits or not because of this character chi of 29. But it's either p squared plus 1 or p plus 1 squared. But there's also another eigenvector, this f, which is lambda minus 2 lambda prime. And when you compute its numbers, you get all these numbers here, -1, 1, 9, 4, 17. Okay, so again, we try to match them with a modular form, as we used to. Maybe, well, we see that these numbers are not all positive, but still they could be squares because there are modular forms with non-rational coefficients. We look in the LMFDB, and we don't find any classical modular form related to this sequence. But we do find a Hilbert modular form. So I'll just click here. Let's hope that it works. Right. So if you look here, we don't know yet what this object is. I'll try to enlarge that somehow. Better? Thank you. So before I tell you what this object is, it's just something I found in LMFDB that matches my data, which is a great way to work. So, so this is the prime 2, which has norm 4, and the eigenvalue is -1. If you remember, our slide said that A2 is -1. This is the prime 3, which has norm 9, and eigenvalue 1. Our A3 was 1. Now, over 5 and 7, something else happens. These primes split over this field. This field is q square root 29, not a coincidence. So here the eigenvalues are -3 and -3, and 2 and 2. And what we are seeing is 9 and 4. Okay, so we just see their product, which in this case is also the square, but that's something else. So we get a very similar phenomena to the one we saw with the classical modular form, only now with a different object, with a Hilbert modular form. So before we go on, I have to tell you what this Hilbert modular form is. So this time it will be more difficult to draw, but I think you'll get the point. So we have some real quadratic field, such as q square root 29. Then it has 2 real embeddings. Okay, we can embed it into R in 2 ways. And we'll be interested in totally positive elements. If you remember, to act on the upper half plane, we needed the matrices to have positive determinant. So when we have more embeddings, we will need to be positive in every embedding. And I'll write k greater than 0 star for the group of totally positive elements. And then we can form the 2 by 2 matrices whose determinant is totally positive. So this acts not on the upper half plane, but on the product of 2 copies of the upper half plane. We just embed it differently into each copy. Right? We have 2 embeddings, and we can act by each of these 2 embeddings on a different coordinate. And that's why it's difficult for me to draw. It's a complex surface, which is a 4-dimensional manifold. And I don't know how you think about these things. Maybe Avi can draw them. I'm not that good. Anyway, the point is that it's very similar to what we had in the classical setting. And again, we can look at corresponding spaces of functions or equivalently differentials. And we can define a Hilbert modular form to be some function having a nice transformation with respect to a discrete subgroup of these 2 by 2 matrices over this quadratic field. So this is a somewhat of a natural extension of the notion of classical modular forms to other number fields. Any questions about Hilbert modular forms? Yeah, you're right. That should be determinant gamma 1 inverse determinant gamma. Yeah, you're right. It's just a typo. Other questions? Okay. So now we know that the thing we should be looking for, or we hope that the thing we should be looking for is something of the sort of Hilbert modular forms. We want to have a bijection between orthogonal modular forms, these spaces that are easily constructed, and we have nice Hecke actions on them, and these spaces of Hilbert modular forms. But it's not that easy. So consider this example. This is a quadratic form with discriminant 40. Well, I could say up front that I don't expect any bijection if I just look at all the modular forms. If you remember, for orthogonal modular forms, we have one Eisenstein series. And in fact, for Hilbert modular forms, we have many Eisenstein series. So I can't really see how to get all the Eisenstein series. But maybe at least on the cusp form side, yeah, at least we can get all the cusp forms or some bijection on cusp forms. But in this case, if we look at the dimension of cusp forms for the orthogonal modular forms, we just get 1. And if we look at the cusp forms, the Hilbert cusp forms for this field, z square root 10, so z square root 10 is the ring of integers of q square root 10, then it is 2-dimensional. And in fact, if we take the theta series of these orthogonal modular forms that you see here, then one gets some cusp form, but it's not an eigenform. So the space of classical modular forms is also equipped with Hecke operators that commute, and they have common eigenvectors, and these are called eigenforms. So far in all the examples we've seen, when we took some eigenform from the orthogonal modular forms, we got an eigenform for a classical modular form. This no longer happens here. And the reason that we have this mismatch in dimensions is because there is a different lattice, which is not locally isometric to our lattice everywhere, but it is locally similar to it. Okay, so when I say similar, I mean I could take the Gram matrix and just multiply everything by a constant. And these lattices also belong into this vector space in some natural way. So we have to extend our notion of the things we consider. Instead of considering the genus, we have to consider some larger vector space to actually get something interesting. So for that, instead of considering isometries, we consider similarities. So we consider all the maps on our vector space that don't just preserve the quadratic form, but they preserve it up to a constant, up to this mu of g here. And we say that lattices are similar if there's some map that maps one lattice to the other, some similarity of our vector space that maps one to the other. The similitude genus, like the genus, is the space of all lattices that are everywhere locally similar to our lattice. And again, we take a class set, a corresponding similitude class set, that classifies all the similitude classes in the similitude genus. And again, it is finite by similar arguments, not isometric arguments. This leads us to the main theorem I want to present today. So this is joint work with Dan Fretwell, Colin Ingalls, Spencer Sackard, Adam Logan, and John Voigt. And I should mention that this all started from a summer project of Spencer. So Spencer was an undergraduate student when it all started. He did a summer project, and it drew more and more people in. And now it's a really nice and large project. And we actually do things for higher ranks than 4. But I think the rank 4 case is the one that is most complete. We actually started off when we said, OK, the rank 4 is known, and then realized that it isn't. So it took some work to realize. So there's a bunch of notation here that I have to walk you through. But basically, the idea is that if one takes the orthogonal modular forms in this new sense, corresponding to groups of similitudes, so cusp forms corresponding to GO, the general orthogonal group, they are embedded naturally into a space of Hilbert modular forms. And we can explicitly describe this image. It's not just some embedding. We really know exactly what the image is. So here's some explanation of the notation over here. So D0 is a fundamental discriminant. Okay, so our discriminant is usually not a square, but we can take out only the square-free part and get the fundamental discriminant. And we have to be a little careful because, for example, the fundamental discriminant of q square root 2 is 8. Okay, so if we have discriminant 8, then D0 is just 8, and n is 1. So the field where we find the Hilbert modular form is q square root d0, corresponding to this fundamental discriminant. Now, you might ask, what happens when d0 is 1, when our discriminant is a square? So what happens in this case is that this is no longer a field. Okay? This is just q adjoining the square root of 1 in the sense of an algebra. So it's a two-dimensional algebra over q. And the Hilbert modular forms in this case is just tensor product of spaces of classical modular forms. So that's the reason we saw the squares before, because basically we were tensoring f with itself. And we got the product of the eigenvalues. Okay, what is GK here? So GK is the Galois group of our quadratic field. It acts naturally on the space of Hilbert modular forms. You can think of it as swapping the places of the primes. Like we had 2 primes above 5 in the q square root 29 case. So we just swap the eigenvalues corresponding to them. So instead of having an embedding into the space of Hilbert modular forms, we get an embedding into the space of Galois orbits of Hilbert modular forms. Okay. And D here, if you look at the image, I'm telling you that these are only D new forms. So D is the product of all the anisotropic primes. We're getting only the forms that are new at D. What? Okay. Now, I also have this notation here, W equals epsilon. So for primes that divide our level n, we have a set of numbers, epsilon, called Witten invariants, and we just set them to -1 if this prime divides the discriminant, and like this D, the product of the anisotropic primes, and 1 otherwise. This is just a set of numbers, like 1, -1, 1, -1. And these W's are the Aitken-Lehner involution. So if you remember in the beginning, when we talked about theta, we talked about how it transforms under certain operators. We still have them here. And there was a remark that it also fixed under the map z to -1 over 4z. So this kind of map is called an Aitken-Lehner involution. It doesn't live in SL2z, but it does act on the space. And we have such Aitken-Lehner involutions for the primes dividing our level. So for each of these, I set a sign, such an epsilon. Okay, so I'm only looking at the Hilbert modular forms whose Aitken-Lehner signs are fixed by this choice of epsilons. Okay, maybe the easiest case is if we're just in a square discriminant case, then D is just 1. Then D is just the square root number. For example, in the 11 squared case, D is just 11. And we're getting exactly these forms whose Aitken-Lehner sign is -1 at 11. Okay, so our image of these orthogonal modular forms is exactly the orbits in this space of D new forms with specific Aitken-Lehner signs. Yeah, that's the end. Yeah, I mean,